Welcome back to Calculus 1. In the previous section, we developed the basic differentiation rules and used derivatives to describe rates of change. We now extend those ideas to functions formed by multiplying or dividing other functions. We will also complete the basic trigonometric derivative formulas and then differentiate functions more than once to obtain higher order derivatives. Together, these ideas allow us to differentiate a much wider variety of functions and to describe quantities such as velocity and acceleration. Let's get started. Here's what we will cover in this lesson. First, we will develop the product rule and the quotient rule. We will then add derivatives of tan of x, cotan of x, secant of x, and cosecant of x. Finally, we will introduce higher order derivatives and connect them with position, velocity, and acceleration. Up to this point, we differentiated sums term by term. Products and quotients require their own rules because differentiating the two parts separately and then multiplying or dividing the results does not generally give the correct derivative. The main question is this: when a function is built from two changing functions, how do we account for the change in both? Let's begin with the product rule. Suppose y is a product of f of x and g of x. Both of these factors may change as x changes. The derivative must account for the change in each one. The product rule states that y prime is equal to f of x times g prime of x plus g of x times f prime of x. The first term keeps f of x and differentiates g of x. The second keeps g of x and differentiates f of x. The two contributions are then added. This is why the derivative of a product is not simply the product of the derivatives. For example, x squared times x cubed equals x to the power 5. And d dx of x to the 5th is 5x to the 4th. Multiplying the two derivatives instead would give 2x times 3x squared, which is equal to 6x cubed. Since 6x cubed is not 5x to the 4th, that shortcut fails. The product rule includes one term for the changing in each factor. Let's apply the product rule step by step. H of x equals 2x squared plus 3 times x minus 5. The first factor is 2x squared plus 3, and its derivative is 4x. The second factor is x minus 5, and its derivative is 1. d dx of 2x squared plus 3 is equal to 4x, and d dx of x minus 5 is equal to 1. Substitute these four pieces into the product rule. H prime of x is equal to 2x squared plus 3 times 1 plus x minus 5 times 4x. Multiplying and then combining like terms gives us h prime of x is equal to 2x squared plus 3 plus 4x squared minus 20x, which is equal to 6x squared minus 20x plus 3. This particular product could also be expanded before differentiating. The product rule gives the same result and establishes a method that still works when expansion is not practical. Some products cannot be simplified by ordinary algebra before we differentiate. Consider y is equal to 4x cubed times cosine x. The two factors are 4x cubed and x and cosine of x. Their derivatives are 12x squared and negative sine of x. Applying the product rule gives dy dx is equal to 4x cubed times negative sine x plus cosine x times 12x squared. Rearranging the terms gives dy dx is equal to 12x squared cosine x minus 4x cubed times sine of x. The negative term comes from d dx of cosine x, which is equal to negative sine x. Because both factors depend on x, both must contribute to the derivative. Now let's consider a function written as a quotient. Y is equal to f of x divided by g of x, where g of x is not equal to 0. Because both the numerator and denominator may change, we need a rule that accounts for both. The quotient rule states that y prime is equal to g of x times f prime of x minus f of x times g prime of x, and this whole thing is divided by g of x squared. In the numerator, g of x multiplies f prime of x, and then f of x times g prime of x is subtracted. The entire expression is divided by g of x squared. The order of the two products matters because subtraction is involved. Also remember that the original denominator cannot be 0. Let's apply the quotient rule to the following function. Y is equal to 3x plus 1 divided by x squared minus 4. Let f of x equal 3x plus 1 and g of x equal x squared minus 4. Then f prime of x is equal to 3 and g prime of x is equal to 2x. Substituting these pieces into the rule gives us dy dx is equal to x squared minus 4 times 3 minus 3x plus 1 times 2x, and this whole thing is divided by x squared minus 4 squared. Keep the denominator squared while simplifying the numerator. 3x squared minus 12 minus 6x squared minus 2x is equal to minus 3x squared minus 2x minus 12. Therefore, the derivative is dy dx is equal to negative 3x squared minus 2x minus 12, this whole thing divided by x squared minus 4 squared. The original function is undefined at x is equal to 2 and x is equal to negative 2. Therefore, the derivative formula is valid only when x is not equal to plus or minus 2. Before applying the quotient rule, check whether the expression can be simplified. Consider y is equal to 6x cubed plus 2x divided by 4. The denominator is the non-zero constant 4. So divide each term by 4. That would give us y is equal to 3 halves x cubed plus 1 half x. The function can now be differentiated term by term. That would give us dy dx is equal to 9 halves x squared plus 1 half. The quotient rule would produce the same answer, but it would add unnecessary work. The form in which a function is written should guide the method we choose. Now it's your turn. Differentiate each function. Before applying a rule, identify the structure of the expression. Decide whether it is a product, a quotient, or a function that can be simplified first. Pause the video now and work all 4 problems. Then continue when you are ready to check your answers. Let's check the answers. For problem 1, the product rule produces 2 terms. After simplifying and combining like terms, the derivative is y prime is equal to 5x to the power 4 plus 3x squared minus 8x. For problem 2, both x cubed and sine of x depend on x, so the product rule would give us y prime is equal to 3x squared sine of x plus x cubed times cosine of x. For problem 3, the two products in the numerator of the quotient rule simplify to 11. That would give us y prime is equal to 11 divided by x plus 3 squared. X cannot equal negative 3. And for problem 4, first rewrite the function as y is equal to x plus 4 divided by x. The simpler form can be differentiated term by term to give us y prime is equal to 1 minus 4 over x squared, and x cannot be 0. Although the functions have different forms, each solution begins by recognizing the structure before choosing a rule. We already know the derivatives of sine x and cosine x. We can now complete the basic trigonometric derivative formulas. d dx of tan of x is equal to secant squared of x. d dx of cotine of x is equal to negative cosecant squared of x. d dx of secant squared is equal to secant squared times tan of x, and d dx of cosecant x is equal to negative cosecant x times cotangent of x. These formulas can be derived from rules we already know. For example, write tan of x as a quotient. Tan of x is equal to sine of x over cosine of x. Applying the quotient rule and using sine squared of x plus cosine of x is equal to 1 gives us d dx of tan of x is equal to cosine squared of x plus sine of x squared divided by cosine of x squared, which is equal to secant squared. Because secant squared of x is positive wherever tan of x is defined, tan of x is increasing on each interval of its domain. Also notice that the derivatives of cotan of x and cosecant x both contain a negative sign. Let's apply these new trigonometric derivatives. For the first function, the constant multiple remains in place. Y equals 5 tan of x is equal to dy dx 5 secant squared of x. The second function requires both a product rule, and ddx of secant x is equal to secant x times tan of x. Y is equal to x squared secant x, then the derivative of this would be dy dx is 2x secant x plus x squared secant x times tan of x. For the third function, ddx of cotan x is equal to negative cosecant squared of x. Also, subtracting cosecant x changes its negative derivative into a positive term. So y equals 3 cotan x minus cosecant x, and the derivative of this would be dy dx is equal to negative 3 cosecant squared x plus cosecant x times cotangent of x. The sum, difference, and constant multiple rules still work exactly as before. We are now combining them with the 4 additional trigonometric derivatives. A derivative is itself a function, so it can also be differentiated. The result is called a higher order derivative. The second derivative may be written as f double prime of x, y double prime, or d squared y over dx squared. The third derivative is f triple prime of x. For derivatives of order 4 and higher, we commonly use parenthetical superscripts such as f to the power 4 of x and f to the power n of x. Consider the polynomial. F of x equals 2x to the power 4 minus 5x squared plus 7. Differentiate once to find f prime of x, and then continue differentiating each new result. That'll give us f prime of x is equal to 8x cubed minus 10x. F double prime of x is equal to 24x squared minus 10. If triple prime of x is equal to 48x. And f to the power 4 of x is equal to 48. One more derivative gives us f to the power 5 of x, which is equal to 0. Each differentiation lowers the degree of a non-constant polynomial by 1, so repeated differentiation eventually produces 0. Motion provides a natural interpretation of higher order derivatives. The derivative of position is velocity, and the derivative of velocity is acceleration. In this example, a ball is thrown upward from a height of 6 feet with an initial velocity of 48 feet per second. Its height is modeled by s of t is equal to negative 16t squared plus 48t plus 6. Differentiate position once to obtain velocity. V of t equals s prime of t, which is equal to negative 32t plus 48. Now differentiate velocity to obtain the constant acceleration. A of t is equal to v prime of t, which is equal to negative 32 feet per second squared. At the highest point, a ball changes from moving upward to moving downward, so its velocity is 0. Solving negative 32t plus 48 equals 0 would give us t equals 1.5 seconds. Substituting this time into the position function gives us s of 1.5 equals 42 feet. Therefore, the ball reaches a maximum height of 42 feet after 1.5 seconds. The acceleration remains constant at negative 32 feet per second squared, and the negative sign indicates that the acceleration is directed downward. Now it's your turn to practice the new trigonometric derivatives and higher order derivatives. For problem 1, use ddx of secant x equal to secant x times tan of x. For problem 2, combine the product rule with ddx cotan x equal to negative cosecant squared x. For problem 3, differentiate the polynomial twice. And for problem 4, differentiate the position function twice to find acceleration. Pause the video now and work all 4 problems. Then continue when you are ready to check your answers. Let's check the answers. For problem 1, the constant 4 remains in place while secant x is differentiated. Y equals 4 secant of x is equal, the derivative of this would be y prime is equal to 4 secant of x times tan of x. For problem 2, the product rule accounts for the change in both x and cotangent of x. Y equals x cotangent of x gives us a derivative of y prime equal to cotangent of x minus x cosecant squared of x. For problem 3, differentiate the polynomial ones and then differentiate the result. F prime of x equals 5x to the power 4 minus 6x, and f double prime of x is equal to 20x cubed minus 6. For problem 4, the first derivative gives velocity and the second gives acceleration. V of t is equal to negative 32 plus 30. V of t is equal to negative 32t plus 32, and a of t is equal to negative 32 feet per second squared. These examples combine the new trigonometric derivatives and the higher order derivatives with the rules we already know. Let's bring the main ideas together. For a product y equals f of x times g of x, the product rule gives us y prime is equal to f of x times g prime of x plus g of x times f prime of x. Each factor contributes one term to the derivative. For a quotient, y equals f of x divided by g of x, the quotient rule gives y prime is equal to g of x times f prime of x minus f of x times g prime of x divided by g of x squared, where g of x cannot equal 0. The order in the numerator matters because of the subtraction. Before selecting either rule, look at the structure of the function and simplify when possible. Some products can be expanded, and some quotients can be written in a simpler form. We also completed the basic trigonometric derivative formulas. Finally, differentiating again produces higher order derivatives. In motion problems, s prime of t equals v of t, and v prime of t equals a of t. In the next lesson, we will study the chain rule, which allows us to differentiate a function contained inside another function. Thank you for watching. In this lesson, we used the product rule and the quotient rule to differentiate functions built from two changing parts. We also completed the basic trigonometric derivative formulas and introduced higher order derivatives through position, velocity, and acceleration. In the next lesson, we will use a chain rule to differentiate a function contained inside another function. I'll see you there.